This story starts with a rock that was formed by magma thousands of years ago. When magma exploded from volcanoes, it created a group of compounds named feldspar through the crystallization of magma. Feldspar compounds cover about 60% of the Earth's crust. There are two types of clay that are made from feldspar compounds, primary and secondary clay. Primary clay hasn't been transported through water, meaning the level of contaminants would be low, while secondary clay has been transported by water and will have been in contact with other compounds that will alter the clay's physical and chemical characteristics. Using this resource did not originate till around 24,000 BC, when early human civilizations mixed clay with water and fired it in early kilns, which is essentially a hole in the ground. As time went on, humans began to understand that pottery has many functions that are both decorative and practical. The credit for inventing glazing, which adds a beautiful glass exterior to the pot, is to the Egyptians, while the credit for improving kilns, which led to stoneware and porcelain, goes to the Chinese. Once humans have begun to understand the chemistry behind our world, it allowed for potters to know how the clay can become a mug, for example, through chemical reactions, or how glaze interacts with other glazes and the clay to form glass coatings. Most potters prefer to learn through trial and error. Clay has a crystalline structure that was formed by a hydration reaction with feldspar compounds and water, where it produces clay minerals and other byproducts. These byproducts are produced due to the presence of CO2 in the rain that has dissolved some of these compounds into clay over time. Here's an example of this reaction. Feldspar is made from aluminum silicates mixed with alkali and alkaline earth metals. Three examples of clay minerals that can be made in this reaction are keelanite, illite, and bentonite. Keelanite has a chemical formula of aluminum oxide times 2 silicon oxide times 2 waters, and has alternating layers of silica and hydrated alumina. The alumina layer has hydroxyl groups attached to it that make weak bonds between different layers in this clay mineral, but they also make strong bonds within the sheet. As the clay dries, the water molecules evaporate, and this creates stronger hydrogen bonds, which allows for the clay to become relatively stable, as it will not engage in many chemical reactions that will alter its form. Illite has 3 layers as well: the silica layer, alumina layer, and an inverted silica layer. This group of 3 layers will then be bonded to the next group of 3 layers with an ionic crystal structure that contains potassium ions and oxygen molecules. This will create strong bonds between those layers. Bentonite has a chemical formula of aluminum oxide times 4 silicon oxides times 2 waters. Its layer ratio is silica, alumina, silica, and water. The water bonds each layer to the next layer. Due to water being what holds this mineral together, when it is added to sodium, the resulting compound will absorb a lot of water and therefore is used to suspend clay's components in water. This clay mineral resembles flakes instead of plates, like keelanite and illite. So the clay has been bought by the potter and is ready to use, but the journey of the piece has just begun. The clay needs to be molded into the desired shape by either hand building or using a potter's wheel. The clay then begins the process of being dried, fired, glazed, and fired again. The first stage of drying is called atmospheric drying, where all the moisture from the air is dried out of the clay. If there's any atmospheric moisture present when the clay is put into the kiln, the moisture will turn into steam, and it will escape from the clay and cause cracks in the piece. Clay goes through a dehydration reaction once in the kiln, where the water that was added in the hydration reaction I mentioned earlier is removed. At this stage, the clay can no longer return to a lump of clay. During the firing, all sulfates and carbon in the clay are burnt off, and the quartz molecules rearrange themselves and cause swelling in the pot. The clay layers continue to bond with each other. The chemical equation for this reaction is the dehydration reaction, and it will create an ester. Here is the reaction. Clay has some unique properties that will allow it to be used in many different fields of work outside of the arts. Clay can withstand very high temperatures without deforming. It is also a poor heat and electrical conductor, so it can be used as a heat and electrical insulator. Clay is used to make spark plugs, engine parts, and even in the nose cones of spacecraft. After the clay has been fired for the first time, the potter must gather their pieces from the kiln once it has cooled down and clean the pieces. This is important because if there's any dust or any of the bits on the clay, it will interfere with the chemical reactions that will take place once the glaze is applied and is being fired on. Glazes add a decorative glass coating that can also be functional, as it makes the piece food safe. When glazes are fired in the kiln, they change their chemical composition, and that allows them to fuse to the clay. These glazes need many things so they can successfully fuse to the clay, such as silica, aluminum, flux, refractory material, and metal oxides for color. Silica is referred to as the main body of the glaze, as it is the vitrifying element / glass former. Vitrification is the partial fusion of the clay. As the firing process proceeds, the solid components are replaced by the liquid components, which is the glass in this case. This process helps the pottery's ability to not absorb water once fired. Aluminum is used as a stabilizer in glaze as it reacts with silica to make aluminum silicate, which makes the glaze less runny, or it adds to its viscosity. Flux is made from alkali and alkaline earth metal elements that help lower the melting point of the glaze and helps fuse the glaze to the clay. The refractory material, usually clay, is used to help harden the glaze and also stabilize the glaze. Metal oxides are used to provide color. The metals that appear on the top row of the transition metals have several oxidation states, which affects the color that the glaze will produce. Having several oxidation states means that a number of oxygen molecules can bond with the metal elements to make metal oxides. Another factor that affects the glaze's finished color is whether the pottery was fired in oxidation or reduction conditions. Oxidation conditions will mean that there's enough oxygen in the kiln for it to react with the fuel source and combust. Reduction conditions mean that there wasn't enough oxygen in the air for combustion, so the flame in the kiln will take the oxygen molecules from the clay and glaze, which will produce a different color in the end result. Take iron for example. If there's limited oxygen, more carbon monoxide will be produced. If the iron 3 oxide has a low enough concentration, it will move to a lower oxidation level. So the carbon monoxide will reduce the iron 3 oxide to iron 2 oxide. The color that we see is the wavelength that has been bounced back from objects because they do not absorb them. The light that is absorbed by the object will have extra energy to deal with since light is a form of energy. In glazes, transition metals are used for their color, but also because they lack a full outer shell, which allows their electrons to move in between energy levels. Transition metals have s orbitals as their outer shell, but there's also half-empty d orbitals in the second to last shell. As light passes through pottery or the glaze, the electrons will absorb the energy from the wavelengths, and this will allow the electrons to move up to higher energy levels. In this case, it will help the d orbitals to be filled. When transition metals bond to make oxides or silicates, they do two things. Their electrons split, and their molecular shapes change. The electrons that are on different energy levels will be split, and this will create an energy gap. For electrons to reach what is called the conduction band, they must absorb enough energy from wavelengths to jump across the energy gap. The energy gap also corresponds with the wavelength of a certain color. Transition metals also can change their molecular shape into an octahedral or tetrahedral shape. These shapes will affect the electron cloud that surrounds the metal, which will affect the wavelengths that can be absorbed by the metal or not. Overall, many different elements have a key role in the production of glazes and whether or not they are successful. Here is a quick summary chart that simply explains the role of the most common elements used in glaze recipes. In the end, the potter takes their piece out of the kiln after the glaze firing and hopefully finds a beautiful piece to add to their collection.